I will just write the equation. If you have any questions, ask me. I will say. Our objective in this class is to understand MG1 system. To understand this KV system, actually we covered the whole chapter. The objective of the chapter was to consider a stochastic process where interval times are not done. So similar thing is here. The unit system has a service time which has a generic solution. If it has a generic solution, then actually it is not marketed and many things that we apply. This is first thing. That's why actually you need to read the chapter. Second thing is that when we start in the unit system, our objective is to know average number of customers, average waiting time in the unit. This is average number of customers in the system, average number of customers in the unit. This is our utilization in media. The calculation of these requires actually one important thing. This can be calculated in very different ways. The book calculated this one either way, which requires to understand one thing. That actually is the remaining time of the scenario appears to understand that let's consider. Actually, we need to solving this equation. We need value of this one, the expected time, expected residual time of an regular process of the next period. And let us consider an example here. The title could be the random incident and recipient. What is random incident? Let us consider the renewal process here. The renewal process actually is a of the is greater than 0. Here actually the renewal times or the interval times are here. Okay, is greater than 0. Here this is the process, this is the time when the process starts. And this is the first renewal, when the first renewal starts. This is the second renewal, and the second renewal time and so on. Right? You can consider this scenario something like you are waiting in a process process. These events actually are the time of the arrival process or the arrival times of the process. And as a result, you arrive in a particular interval period, this one, that is the main period, from tk1 minus to k. And this is your arrival time. One thing that you consider here is that the interval times are not exponential. Interval times are not exponential. So, if you consider this is the interval time x2, this is x1. In general, what we assume that xn actually it has a distribution of this is a general. It is not primarily exponential, but it can be exponential. And let us consider this variable is not time. Let's say this is the time quantity R, actually we assume that this R is a random variable whose represents the amount of time the customer, the passenger has to wait. We call it the residual time of the renewal. That is the time that actually the renewal will take. Last renewal occurred here, the next renewal will occur here, and the customer arrives exactly at this time. This amount of time is the time that we need for the next renewal to occur. And our objective is to calculate the expected renewal of residual time. Okay, so the quantity that we need to consider are the distribution of the internet traffic. So what we assume, we only assume that x is a random variable, it has an expected value, it has a second moment. Both of these are finite. They are not infinite. These are our assumptions. So any random variable can be. Now the second quantity of interest that we have to actually deal with is the gap of the current interrelated time. This is the now a very natural question is what is the difference between x and w? X is the random amount of time. X is the random amount of time. You mean the interval between any two. So it is x1, it is x2. Even this one is xk. So if xk is already there, the very important question here is why w is the question here. In reality, what happens? That happens to me many times. Whenever I go to the bus stop, suddenly buses stop now. Do you feel that? Usually you will see there are many buses. Every 2 minutes or 3 minutes, they are passing by. And whenever you are there, guess what? You will find last 10 minutes you have been waiting there and the bus is not there. So is it a logical thing or it is just a coincidence? Coincidence. It is logical. And mathematically we will see. Why is it logical? Because actually majority of the people go to the bus stop during the rush hour. And when you are not going somewhere in the rush hour, that means you are out of the rush hour and in regular time, actually you don't care about the delay, and most of the cases you do not notice it. At that time the buses are very good. But when there is a rush hour, traffic increases. So speed lowers down and internet. That's why our fee is all the time is there. The waiting time for a bus is always larger than the average interval time. And it is the fact. On the other hand, when we actually find the distribution of x, we consider many such intervals, hundreds, thousands. Then we are actually predictive properties are accumulated in the randomness of x. That's what usually you do because it averages the unusual cases. Out of 24 hours, you will find rush hour 2 hours in the morning, 3 hours in the afternoon or evening. But out of 24 hours, actually it is a small amount. Anyway, that's why what happens, the random variable x is many cases have an average distribution which is smaller than the gap where the random customers. That's why we are assuming here the gap between successive buses where a passenger became the random passenger, that passenger is going to actually take a bus. This is clear. Now, we will find out what this point, the expected value of R, what will be your expected waiting time. It is obvious that your waiting time in a rush hour will be higher, larger than your waiting time in a because whether they are of the same distribution or not, your waiting time will be. So we will be actually calculating the waiting time of the random variable. To calculate the random variable, the expected value of the random variable R, what we need to do, we have four random variables here: X, W, R, okay. We have three random variables. The random variable X always will be given. It has a general distribution, but we know the random variables. Somehow we need to connect the random variable X to W. If we can connect X and W, then we can calculate the distribution of W. Once we will have the distribution of W, then we can connect W and R. Even actually they are physically related. R should be always less than W. Correct? Always. R cannot be greater than W. And so, we will actually find a conditional distribution of R given W. Since we know W, and if we can find the conditional distribution of R given W, then we can find out the joint distribution of R and W. Once we have the joint distribution, then we can calculate the marginal distribution of R. And from the marginal distribution of R, we can calculate the expected value of R. This is the steps we know the distribution of X. We will relate X with W, and from that we will calculate the distribution and expected value of W. Then W and R are connected. We will calculate the conditional distribution of R given W. Then we will calculate the joint distribution of R and W. Then from the joint distribution, we will calculate the marginal distribution of R. We have actually practiced many examples in the fourth semester that deals with this one. The joint distribution and the marginal distribution and the conditional distribution. So the first thing that we will consider there, we'll consider the probability. What is the probability that a customer, the W starts from here, arrives in an interval which is in between W and W plus, that is we are talking about this. So what is the probability that a passenger arrives at the bus stoppage during this interval? So occurs between W and W plus W. So if you know the PDF of W, can we calculate this one? If we know the PDF of W, then actually we can calculate the PDF at point W.
Sir, can you explain RW and V once more?
Sorry?
Can you explain RW and V once more?
R,
W and V,
R,
what
W,
they each represent.
This is the K minus 1 limit and this is the K. You can consider that from a random passenger's perspective, this is the last bus and this is going to be the next bus. Right? At a particular random point of time, which is uniformly distributed in between these, we assume that this interval is and the customer actually appears at this point. Now, the amount of time the passenger has to wait to get the next bus will be this one. We denote this one by R. residual time that the center will work. And the amount of time between the arrival time of the customers and the arrival of the previous bus actually is divided by time. So now we have W, D, and R. Another quantity actually that exists is X, which is the, say, first arrival, second arrival, third arrival. These are actually inter-arrival time. We call them, this one is X2, this one is X3, they are IL. So we denote them the solution by X. This is the inter-arrival time. As I mentioned, that this X actually is defined considering the inter-arrival time of all the buses, say, in the day. Whereas we are considering the inter-arrival time here only for this many customers, say, this, that customer. So usually it will be not. That is our assumption. Now you understand? So once we have this in mind, then since this is W, a random amount of time, it has a distribution. What does it say? It says the probability density at this period. Right? Because, and we assume that this length is small term. This one is capital number, right? Now, if this is the probability density, that means probability per unit length. If we multiply this one with a small length beta, then what is the product? It doesn't matter. If the probability density here is 5, that means 5 unit per minute, and we have an unit of 0.1, then what is the probability in this 0.1 unit interval? 5 into 0.1. This is simple, right? We did this one very many times. So, this one multiplied by W gives us the probability that the customer arrives in between W and W plus BW, starting from the last arrival time of the bus. Now, this W is, we are going to connect this W with, X with the W. But actually the books assumes that the probability density of W, since it is pointer, and the probability density of X at any particular point, if you measure, then actually as it goes away from the starting point of W, then actually the X will have less probability, but the W will have higher probability. Is this clear? For example, if we consider the exponential variable, the one that actually will be defined for a smaller result and the one that will be defined for a larger result. Because the area under the curve is small. So as you go away, then actually X will be less than the W. If you come here, X will be higher. That's why they actually assume that. I do not have the clear actually idea yet, but I just believe on them that this probability, and if we measure the same probability from, at a distance from this one to W, the same distance W, but the first one is measured based on the distribution of W, the second one is measured on the distribution of X at similar point, and we multiply it by W. So both of these two are now representing probabilities. But we are measuring this probability from two different distributions. And they are saying that actually this one, as the distance from the starting point of W will be increasing, the probability lower one will be decreasing. That's why what they call, they multiply it by W. So when W is less, they are considering a a smaller portion of x as equivalent to this one. When actually W is increasing, the probability getting pi in this equation of x will be decreased. So a larger value of W will multiply. This is clear idea, and I think it is acceptable based on this. Now, even then, what they assume that these two probabilities are not exactly equal. They are proportional. That means when this one will increase, the other one will increase. When this one will increase. But when we will make it equal, then what we need? We need a proportionality constant. Let's say beta is the proportionality constant. So, to calculate the distribution of W, what we need to do? We need to start that we have a relation something like this. So, since these two are equal, then we can. Then what we get? We get the PDF of W for the value W is equal to PDF. So beta multiplied by W the PDF of X for the value. Now if we take the integration of both sides, they will be equal, right? And then what is the value of this? You are integrating a PDF from minus infinity to plus infinity. What will be the sum? Okay. Now, if we write this one in this way, say beta is a constant from minus infinity to plus infinity. What we are doing here? PDF for a return variable is multiplied with the value W for which the PDF is calculated, and then we are doing it from minus infinity to plus infinity. For these possible values W, we multiply W with this PDF. Then this one is what? Any volunteers here? It is the expected value of random variable X. If you go to the definition, then you will find expected value of X is the integration of its period multiplied by the value for all values of X. Then, if you relate now this part and find that 1 is equal to beta times expected value of X. So, what is the expected value of X? Sorry, my mistake. We need the value of beta, not the expected value. The proportionality constant actually eventually becomes what? The proportionality constant actually becomes 1 over x. Then what is the distribution of x? In PDF? Just come here, not here, here. If we come here, then the PDF is W time f of x for the value W. So the relation between the random variable W, the PDF of W, and the PDF of x for the same value W is answer. Right? It is actually a fraction of the PDF, the fraction calculated by multiplying it by W, as I tried to discuss. Actually, I did not explore that one much, and dividing it by value of x. So, if we consider this one for a Poisson case, what do you mean by the term Poisson case? In a Poisson process, interval times are so x is exponential with the In case of question, what we actually would find W f of x for derivative W divided by what?
So this time 1 by lambda.
Right? Because for question expected value is 1 over lambda. And eventually what we find?
Lambda W equals to
W times, sorry, lambda times W, then what is the PDF for this one if it is a Gaussian random variable x? Lambda times e to the power minus
Lambda x.
lambda W, because we are measuring it. Then it becomes W square, so lambda square W times e to the power minus. Actually, this one is the PDF of two R. What is the expected value of a 2 R random variable? If the expected value of x is 1 over lambda, then the expected value of W will be 2 over lambda, W. So that also actually shows that the random incidence time of a passenger usually sees a wider gap between the successive arrival of buses. And it is exactly now. And we will further certify this on just one second. Okay. Any questions up to here? And it is called a random incidence. Now, what we need to calculate is, we need to calculate the distribution of R and expected value. As I mentioned, once we have the distribution of R, W, we can find out the distribution of R given W. Look at here. If W is given, then what is the value of R? Actually, the customer is a random variable. That means all points within this W interval are equal here. And accordingly, this random variable actually is uniform. In between 0 to or what we can do, we can actually write down the conditional PDF of R given W is equal to W, which we usually write in this way. Conditional PDF of R given W for the value R given the value of W equal to W. You know this one, right? Is equal to 1 over W. Alright, actually, the R will be definitely less than W and will be greater than R cannot be greater than W because this waiting time will be in between. Okay, so what is the joint distribution? Can anyone help me here? Joint distribution. Conditional distribution multiplied by the marginal distribution. Right? Now, if we put the values, this one actually is a straightforward what? W from here. And this one is what? This one was the ultimate outcome. Which is? This one is W times the PDF of x for the W divided by expected value of Any questions here? Now our final step is what? How can we find out the marginal PDF if we know the joint PDF?
Integration.
Hmm?
Integration.
Good, very good. So the marginal PDF of R for the value R will be for all values of W. So if we actually integrate the joint PDF of R and W with respect to, right? So this equation has two steps. One is you need to set the limits, and other one is you need to put the values of this. Fortunately, we know the value. This is f of x for W divided by expected value of x times. What will be the limit? Good. W does not control R does not control W. They are not affected by each other. Then, what is this line?
Equals R.
And what is this area? This area actually are the points where R is less than. And our condition says R should be less than. This is first. Second thing says we need to calculate the value or the gradient for a value R. Say let's this is R. And this is the summation of PDFs for all points. Value is R. Other value of W will go from minus infinity to plus infinity. W cannot be here. So W will start from here and we will go up to. What is the starting point? For R, it should be R. Because on this line, R and W are equal. Okay, so the limit will be from R to
Infinity.
if you do this, actually this part following the text and unnecessary part becomes what? The complementary CDF of x, right? Divided by E of x. But we do not need it. Then what is the expected value of R? This is put here. The expected value of R. By the way, you got the slides. The expected value of R is equal to what? For all values of R from minus infinity to plus infinity, we need to multiply R with its PDF. Sorry. Right? And then, next step will be, what is the range for R?
Zero to W. 0 to W.
R will go from 0 to infinity. The E of x is a constant. Let us put it here. Then what we are left with? R times and we need to actually have the this R to infinity, then dW, then dr. You see, just to put the value of the PDF of R from and we take the x is clear. Now, if we look at here, then we will say the outer integral is R, the inner integral is R. But still, this one actually is considering this area. R will go from 0 to infinity, W will go from R to infinity. So is this clear? So the range of R is from 0 to infinity, that means you go in this direction. And this is R, and W will go from R to, yes. So we are still covering this area by the down integration. If we extend the integration, then we will have something like this. 1 over dx. So first we will consider W. W will go from 0 to infinity. Now we are considering first this axis. Then following the text. In this way you can do it, but following the text so that it will be easier for you. Then what will be the integral for R? Once W is selected, R will be from 0 to then R f of x for the W. First we have dr, then now dw. Because this is the limit for W. And this actually solution is very simple. The R will be R squared by 2 first because this W1 will be fixed. Then you will have actually all the limits with respect to W. And because the limit is from 0 to W. And I am not going through the derivation, I am immediately writing it, right? This one is the second moment of x divided by 2 times the first moment of x, but that is 2. So the expected value of R is the second moment of x divided by the first moment of x. You can easily solve it if you have any problem. Just let me know in the. Okay. So once we have this one, then if we consider the Poisson case, what is the relation between R and X? The expected value of X is what? 1 over. And when we are considering the Poisson process, then what is the expected value of R? This one. E of x square is equal to what? 2 by lambda square. And E of x is 1 over half into lambda. Then it becomes, so in principle it can be shown that R and X have the same distribution. What does it mean? So, if we look back to the figure, the X should start from here, right? And R should start from, if they have the same distribution, means X actually, R actually forgets its past. That's why, or X forgets its past, and then we will consider. That's why actually the random variable X is memorized here, and X and R eventually becomes the same distribution. Okay, so this also proves the memorized property of the exponential random variable. So what is our takeaway from here? For MZ1 cube system, the takeaway is the expected value of the residual time to the variable or the waiting time, mean waiting time for a pass actually is the second moment of the interval time divided by 2 times the we will be using this one in calculating different parameters of the ANG1 unit system. That will make our life very easy. There are different ways of calculating this one. Some uses the characteristics functions, some uses moment generating function, some uses other techniques. So most of actually throughout the course, I try to avoid the moment generating function. You will find many equations that are related to moment generating function or characteristics function in the book, but I try to avoid it. In some cases, I did not consider it. For example, the distribution of the weighting guide. For none of the Cubic system actually we discuss this and we will not do. If you need, you can. Edit, I think you will be able to understand it by yourself. Okay, this is not very difficult. Especially the calculation and derivation, those use the moment generating function or characteristic functions are much easier. So NG1 is a unit system where the arrival time is Markovian. So we have the arrival equation, is a Gaussian process. So we write later. The service time is not exponential. It has a general distribution. We do not know. However, what we assume the expected value of this distribution x service time and the second moment both are finite. They are less than infinite. Number of servers, the one indicates number of servers is 1. Population size is infinity. We will assume that from an infinite population, customers are having to the unit system. System capacity is also in infinity. That means only one customer will be accommodated in the server. All the remaining customers will be accommodated in the queue. So queue has an infinite capacity. The queue discipline is default. So all these three are defaults. Our objective is to calculate the expected number of customers in the system, which actually is E of n. Expected number of customers in the queue, expected waiting time in the queue, and so on. Right? We will calculate one, and then we will calculate O2. We will use the Newton's formula to actually derive the values for the other. Right? The service time distribution is x, so the PDF is this one. Instead of the queue at time n is np. If you understand. Now we will go here. Instead of the queue is np. Question is this np is it a partial process? To be a partial process, what we need that the service time is. But we already mentioned that the service time is what?
General.
Having a general distribution. Right? Then the next state of the process depends on two things. One is what? The current state. Second one, remaining time to the next transition. Like the past cases, actually how long the process will further wait in the current state plus the current state is required to know the next state of the process. And these parameters from Markov are the Markovian property is not satisfied. object with force to satisfy the Markovian process. If we can define a two-dimensional stochastic process like A of T and R. For in fact R of T. This two-dimensional stochastic process actually is a Markov process because the current value of N of T and the current value of R of T will explicitly define the probability that what will be the next successor of the process. But the problem is the N of T is a discrete random variable, whereas the R of T is the remaining time, every single moment, the remaining time is decreasing by 1. So it is a constant. Or even if the state is 1, that means you are in state 1, you will have many states. You have infinite number of states. That's why the processing of the Q system is very complex. And we want to avoid it. We will consider the continuous state processes when actually hopefully we will cover a number of processes that were not needed in the course plan previously. For example, the random walks, then Brownian motion, then diffusion. So all these stochastic processes are trying to cover, but I know even if there is time, we can actually explore the diffusion model. Okay, if there is what and if I can know. If you cannot, then next step. So the continuous state process that are a bit difficult because we need to use what is this? It has a closed bracket. Right, ODPD, right? So actually this PD sometimes it will be a statistical differential equation. A lot of stuff I actually studied 30 years, 35 years there, 30 years there. Okay, that's why whether I will be able to manage it, I don't know, but I will try to cover it. And there is another, by the end of this week, you need to form the group. 5 minutes group, and you need to say that. Okay? And carry towards it. So, now, for this stochastic process, which is at the beginning not Markovian, then considering it as a 2D process, stochastic process, we can make it Markovian, but it becomes very difficult to deal with. Then we will go for a simple approach. We will consider this two-dimensional stochastic process only when RT equal to, so when you are here, you will consider the stochastic process only when the residual time is here. What does it mean? We will consider the state of the process only when the customer is departing. When the customer is departing, for a departing customer, what is the streaming time? 0. So only we will consider the time point when the customer is departing. At those departing points, actually, we have a Markov chain that does not deal with the residual time because the residual time is always 0. And so we have an embedded Markov chain. embedded markup chain. And for this embedded markup chain, actually, we can deal with anything that we have seen in the last class, right? By now, after this point, do you have any questions? I will finish it in 2 minutes. So the class of questions. You will come to request for 10 minutes. So, what we want to do from here, we want to focus on the diagram. This diagram is very similar to the diagram that we have considered for the random incidence case, waiting for the pass. This is the time axis, this line is time. Right? We are interested about a particular customer. We call this customer the kth customer. And the kth customer arrives in the system in this. If the system is busy at that time, then one of the previously arrived customer will be in service. Let's say that very customer started his service at this point, and we call this ith customer. Then we have actually things. One is we are considering the recently arrived customer, that is the kth customer. The arriving customer will find if the system is not idle. Let us consider for now the system is not idle. That one customer is receiving service. We consider that is the ith customer. And in between I and k there might be many customers, right? What are they doing? They are waiting in the, let's say, the given customer, sorry, kth customer will find this many customers waiting in the queue. So how many customers in the system? One in service and NQK is in. Is this clear? Now, this is the arrival time of the kth customer. The ith customer will leave the system after some time. Let's say the residual service time is R of the ith customer. So, residual service time of the ith customer is Q size at the arrival time of the kth customer is total number of customers when kth customer arrived is this clear? So all of these are all the states of the system. Every single possible state of the system actually is defined based on the arrival time of the kth customer. Any question? Sorry, so little louder.
The term NQK, are we multiplying NQK or?
Very good question. Unless you understand this one, how would you actually process this one? Previously, when we discussed queuing system, we had N is the total number of customers in the system, of which some are in service. In one server, one customer. Two server, at most two customers. Right? Plus, NQ is the number of customers in the queue. If we would write, this would be the variable. This should be a line. And to make it specific, I would have two variables. So what does this variable represent? It is a single variable representing the queue size. That's why NQ at the time of arrival of the. So collectively, it represents a single variable which reflects the queue size at the arrival time of the. Is this clear? Unless you understand this one. Now, what is the waiting time of the kth customer? Very important question. What is the waiting time? Let's say the waiting time of the A customer is divided by W. But it will be starting from here up to what? Two parts. One is the remaining service time of the I customer. Another one, the service time of the all the customers who are in. What is the service time of a single customer? I think I didn't discuss it. So, what is this one? Or don't consider it as convolution. So NQK times RI is always there. We assume, we discuss RI that an arriving customer will always find the server is busy. That means when the server is busy, number of customers in the system is greater than 0, at least one. If at least one customer is there, then the server will be busy. If N2 is 0, then this waiting time will be automatically 0. But this RI will be 0 when there is no customer in the system. And when there is at least one customer in the system, RI will be RI. So let's write this one. What is this UK? This UK is not divided kingdom, it is an indicator function which is equal to 1 if there is at least one customer, it is 0. Right? What is RI? We already know the residual term. What is NQK? Number of customers in the queues when the kth customer arrives. X is the service time of arrangement. We assume that these two quantities are random and independent, and these two are also independent. E of k is multiplied by okay. Why so? If the kth customer finds the system is idle, what will be the value of RI?
0.
If the A customer will find at least one customer in the system, then that customer, if there is at least one, then that customer will be in service. If there is multiple, then one will be in service, the remaining will be in queue. So, unless the system is empty, RI will have a. So, UK will be 1 when there will be at least one customer in the system, and UK will be 0 when the system is empty. When the system is empty, this is when we have some initialization type things, then we use integrator. If we are in the initial state, then this is empty. If we are not at the initial, then we something like this. Okay. Now, if these two quantities and these two quantities are independent, then what we can write is, I'll finish by 5 minutes, inshallah. Sorry for the weird start. There was an example in the video trying to find out the backlog. So just we are actually taking, this is sort of actually the random number of customers. We have a random number of bills. This is sort of compound quotient process, or by using the word equation that we have seen, Gauss equation. Right? What is the value of E of Ri? Right? That was our only trigger. So we can write this one. Right? So however, into what is this one? This is an indicator random variable. So what is the expected value of? It will be 1 into what? Probability that nk is greater than 0 plus 0 into probability that nk equal to 0. Since this second part is multiplied by 0, it is always. And this one is, what is the probability that nk is greater than 0?
Of
Which actually is the traffic intensity. Find it, this is not exponential, this is. So what we can write here? We can write rho. What is this one? What is this one? This one actually is by applying the Little's law. What is the average users? The Little's law says the average queue size is equal to lambda times average here. So this quantity can be replaced by this one and this one is identical. And what is 1 over x? Sorry, x is what? 1 over mu. In the surface state is mu, the expected value is 1 over mu. Then this and this collectively becomes what? So expected value of Wk will be here, if you bring this one in front, will be 1 minus rho. We have 2 times 1 minus rho into expected value of x into E of x squared times rho. Okay? This actually what we have, lambda times e to expected value of Wk times expected value of x. Expected value of x is 1 over mu. Lambda by 1 over mu is what? Rho. Then this rho is multiplied with expected value of Wk. If you bring this one in front, then you have expected value of Wk into 1 minus rho. That 1 minus rho comes here. This 2 comes here. This x comes here. This clear? Now, if we replace this E of x by 1 over mu, then we can further simplify it. Right? This equation, actually, even though we calculate it for the gate customer, it is the general behavior of the system, and accordingly, the experience of the gate customer is typical. Mean waiting time in the MG1 system is in delay is lambda expected value of x or a square. The square, right? The square. Divided by 2 into 1 minus rho. This equation has a name. It is well known as what is this? Some Czechoslovakia people will be there. Polar jet team formula. This will give you the expected number of customers. Expected number of customers or expected waiting time. What is expected waiting time? So I'll finish here. Based on this expected waiting time, now you can apply a lot of things. By applying this formula, you can calculate the expected number of customers, right? By adding with this one row is the expected number of customers in the system, you will get the expected delay, expected number of customers in the total system. From here, you can calculate expected value of NP. Adding this one with this one is the average number of customers in the server. You will find the total number of customers in the system. Then from the total number of customers in the system, applying leader flow again, you will get the total service time, or system time, or schedule time, DL system, right? And also in the book, they have applied one formula to further process the equation. I don't know whether there is any exercise related to that from that one. The exercise actually, the relation that is used there. Those who have completed the course simulation, I think they know it. Coefficient of variation. This is the ratio of sigma x divided by x. Or you can write sigma x, sigma x, let me check. A square divided by p of x square. So by applying this formula, after some simplification, what they did actually expected the second moment now becomes what? Following the text. 1 plus the coefficient of variation multiplied by p of x. By applying this one, they have further simplification of this formula. So that's all. You will check it. I am not showing you the equation for all the variables here. Expected W, expected N2, expected value of N, and the expected system time that will be defined as what? T. But T is actually equal to W plus service time. Expected service time is. So that's all for now. From the next week, on Tuesday, we will start. This Tuesday there will be class, right? Yes.